Hello everyone, my name is Ao, and I'm from Washington University in St. Louis. Today I will be presenting our paper, Tintin, a unified hardware performance profiling infrastructure to uncover and manage the uncertainty. First, to identify the performance issues in a system, we need to profile it. That's why we collect the data about how the system is running. So the profiling can focus on different aspects, such as CPU, GPU, memory, and so on. On modern CPU, there is already a built-in hardware support called Performance Monitor Unit, or we can call it PMU for short. A PMU is composed of a few counters, which is called hardware performance counter. Each counter can be used to monitor the microarchitectural events, such as cache misses, TLB misses. The typical way is that the developer can program the PMU to track specific event of interest. Then each counter in the PMU will track one of those events. While the PMU is originally created for debugging performance bugs, but now it is widely used in other areas, such as online resource orchestration, power analysis, or even some security tasks, such as intrusion detection. And the thing is, there is a long-standing problem with the PMU. It only have a limited number of counters available on the CPU, which is just 2 to 8 on most of the CPUs. And each counter can only monitor one event type at a time. So, but in reality, the number of events we care about is much more than that. It's often like thousands or even hundreds. So this means we can only monitor a small subset of the events we really care. So to work around this limitation, the existing solution uses event multiplexing to solve this. Specifically, in the Linux perf subsystem, it will put all the events in a queue, in a list. Then during one scheduling slice, it will select a subset of these events and then put them on the available counters and measure it. So then in the next scheduling slice, it will rotate all these events in a round-robin fashion and select the next events and then measure these events. So by the end of the profiling, by the end of this measurement, the perf subsystem will extrapolate the total counts using how long it's actually being measured and how many counts for each individual measurements. So obviously there is a problem. Is that this extrapolation, it uses the partial measured results to estimate the full picture. This can lead to very large errors. To look into this, we run a preliminary experiment on this. The experiment was conducted on a machine has 4 available counters. We gradually increase the number of events we measure, and then the result is shown in this figure. We can see once the number of events goes beyond the 4, which is the number of counters, the measurement results varies a lot. This suggests very large measurement errors. So the main contribution of our paper is tackling these long-standing issues. Before I go to the detail of our solution, I will give you some key insights that guided our solutions. There are three main insights. First, the actually the event multiplexing errors can be quantified at runtime. These quantified errors can give us a useful signal to reduce the overall errors. And most specifically, different events, they exhibit distinct levels of errors. So this distinction can allow us to schedule them accordingly to reduce the overall errors. Moreover, since you have to multiplex, so this type of error cannot be fully get rid of. So, but as a profiling tool, you can report these errors to the user space application. So this information can tell the user how confident you are about this measurement. Yeah, here's a simple example. The figure in this slide shows the event count of 2 events during 1 second. Is the bus cycles and the L1 data cache load misses. Yeah, we can see the bus cycles is quite stable. So the extrapolation results, it could be more accurate. But in contrast, the cache misses, it varies a lot. There are 2 noticeable spikes there. So the opportunity is, if we can detect these spikes online, then we can actually allocate more time to the cache misses. So we can reduce the errors of cache misses. And afterwards, we can also report these errors to user space to tell user that this cache misses measurement is not very confident. So based on these insights, we propose Tintin. Tintin is a profiling subsystem built inside the kernel. It has 3 modular components: monitor, scheduler, and manager. These 3 components work together as follows. The monitor, it quantifies the errors at runtime. Then it will report these errors to the scheduler. The scheduler will leverage this information to generate an event schedule. The event schedule tells how long each event should be put on the counter. So, for the manager, it is the interface to communicate with the user. It can handle different user requests. First, let's talk about the monitor. Its main job is to track and characterize the errors introduced by multiplexing. So there is a challenge. The tricky part is that we don't have access to the ground truth of the measurement at runtime. So we can't directly calculate the errors. Our solution to this problem is use the variation as a proxy for the errors. As I mentioned earlier, the standard way to estimate the total count is extrapolation. So there is an implicit assumption of this extrapolation is that the consecutive measurement, they are linear. This means if the 2 consecutive measurements, they are closer to each other, the extrapolation will be more accurate. In contrast, if it varies a lot, the errors is larger. So based on this, we design the monitor. It calculates the measurement variation at runtime and use this to estimate the multiplexing errors. Next is the scheduler. Yeah, for each event, we can actually obtain 2 key pieces of information from the monitor, which is how long an event is being monitored and how variation it shows. Use these 2 factors. Use these 2 factors, we can model its measurement uncertainty. It's just the variation times the unmonitored time. So our design goal is to minimize the total uncertainty of all events. So we can express this into an optimization problem as follows, with a set of constraints. So it is interesting, we found that this problem can be translated to a semantically equivalent to a classic direction in real-time theory. It's called elastic scheduling. So this is great because we can borrow the existing solution to solve this problem online in a very efficient way, and also we can prove the optimality of our solution. And yeah, that's exactly what we did in our paper. We formulate the whole problem using the language of real-time theory, and we give the solution, and we prove the optimality of the solution. And due to the time limit, I will not go to details of that. I will just highlight some other interesting things. Yeah, when we implement the scheduler, we also found some practical challenges we need to work around. First is that online solving that optimization problem is quite expensive. That's especially for the case you have hundreds of events. So we did some small optimization to improve it. First, we used the approximation to force a minimum scheduling quantum such that we can limit the maximum number of iterations in the solution. And we also proposed some heuristics to avoid the costly backtracking. Yeah, that's all for the efficiency. And also for the elastic scheduling, it schedules events depends on the uncertainty of that event. So it means some low uncertainty events may never get scheduled. Maybe that's an issue of our design. So to work around this, we introduce some warm-up phase for every single event to make sure they have enough measurements to initialize the uncertainty. And the last component is the manager. It is an interface to user space application. It can handle diverse user requests, and I think its main novelty is that it also reports the measurement uncertainty to user space application to enforce the measurement confidence. As far as I know, this is the first profiling tool which reports this measurement uncertainty to user space. So we face a natural question, which is how can we make use of this uncertainty information? Is it very hard for existing applications to adapt to it? So to explore this, we did a survey of existing works using PMU data. We categorized the existing works into two groups. One is model-based approach, another is rule-based approaches. Yeah, for the model-based approaches, they are typically data-driven and relies on machine learning models. So in this case, we can simply put the uncertainty information as extra model inputs. And for the rule-based approaches, they are typically procedural logic based on the domain expertise. So in this case, we think the uncertainty can be used as an additional logic check, something like that. Just check if the confidence is enough before you make the final decision. That's all about design. To evaluate the effectiveness of our design, we implement the entire system in Linux kernel, and we evaluated it using CPU benchmarks and also real-world case studies. We also compared our work with the state-of-the-art. There are three key questions we want to answer in our evaluation. That's That is, first, how much can Tintin improve measurement accuracy? Second, what is the overhead of Tintin? Third, how does Tintin help improve real-world applications? So to answer the first question, we evaluate accuracy over the benchmark. We measured the error rates on the different number of events. What we found is that the native Linux perf system, it can introduce over 20% errors when tracking more than 100 events. In contrast, Tintin can maintain this error below 5%, even under the same conditions. As for the overhead, across all the workloads we run, the Tintin does not add too much overhead compared to native Linux perf. On average, Linux perf introduces 1.9% runtime overhead. Tintin increased this slightly up to slightly to 2.4% on average. Third, to demonstrate Tintin's practical value, we evaluated using a real-world application called Pond. Pond is a memory pooling system developed by Microsoft team. Its paper and source code were released at 2023 ASP+ conference. Pond used PMU data to detect the performance interference. So we are going to investigate if Tintin can improve this prediction accuracy. We followed up the original experimental setup in the paper and repeated the experiments 100 times. The results are shown in this figure. Each bar in this figure indicates the prediction score of the model. So the higher score means more accurate prediction results. So higher is better. So first, we compare Tintin with the original profiling tool used by Pond called EMON. EMON is a profiling tool developed by Intel. Yeah. Among the 100 test runs, Tintin outperforms EMON in 95% of the cases. Next, we also looked into how effective our elastic scheduling is. We compared it with a strawman solution round-robin scheduling policy. And the results shows elastic scheduling is more optimal. It outperforms in 64% of the cases. Finally, we also wanted to see is the uncertainty information actually useful. To test this, we trained two models. One is the original model used by Pond. Another one is modified version that we also include the uncertainty as additional inputs. So the results shows that incorporating uncertainty can improve the performance in 55% of the cases. This shows the usefulness of the uncertainty information. Yeah, that's all for the paper. To wrap up, we have three main contributions in this work. First, we propose a method to model and report the measurement uncertainty in hardware event profiling system. Second, we design and implement Tintin. It's a kernel subsystem with three modular components. And we did the evaluation of Tintin across real-world case study and benchmarks. Yeah, that's all for my today's talk. I'm happy to take any questions.